Hello, my name is Petr Svenda, and I will show you how to bypass primality tests on cryptographic smart cards. The paper title is Fooling Primality Tests on Smart Cards, and it's joint work with Vladimir Sedlacek and Jancar. Let's start with some motivation. For Diffie-Hellman key exchange, digital signature algorithms, as well as their elliptic curve versions, some parameters must be prime. If they are not, an attacker can frequently recover the private key via some variant of Pauling-Hellman attack. So it's very crucial. How to make sure that particular parameter is prime? There are two options. One is to construct the number so it's provably prime, but that's time-consuming. Another option is to use Primality, Monte Carlo primality testing algorithm like well-known Miller-Rabin, which the high probability will tell us whether the particle number is prime. But it's only probabilistic, which means there still can be false negatives, so-called pseudo-primes, which are composite numbers that are able to pass this probabilistic primality testing. There are, in the wild, weak implementations of Miller-Rabin test, and these weak implementations can be fooled. It was shown in 2008 by Daniel Bleichenbacher and more recently by a group of researchers against a variety of different libraries in 2018. So what is Miller-Rabin algorithm doing and how we can fool it? Imagine there was a bank robbery with a lot of witnesses. Police is investigating, they have a suspect, and now they are asking randomly selected witnesses whether the particular suspect is a thief or not. And if enough witnesses agree that this is a thief, likely our result is correct. In case of prime testing, likely we do have a prime. But there is a catch. What if the witnesses are not selected at random and suspect had the chance to first bribe these witnesses? In that case, of course, they will say no, this is not a thief, and we will let the suspect go, despite the fact that he is a thief. And this is exactly what can happen in a weak Miller-Rabin implementation, where the witnesses are actually some small tests testing for the primality. And if we're not selecting them by random, one can construct the number so it will pass these witnesses despite being a composite. All this is well known, so the question is, can we now just go through all implementations of primality testing and then just check whether it's correctly implemented? And this is true for red box implementations where we do have the source code. We can just check whether they are using random witnesses, enough of them, and so on. But the problem is with the black box ones, with the devices or implementations for which we don't have source code, and therefore we don't know which particular primality testing algorithm they are using and which particular witnesses they are using. For this, we need to first guess what they are using and then eventually verify the potential attack. An example of black box scenario are cryptographic smart cards. And in our work, we focused on Java card-based cryptographic smart cards, which is currently the dominant open platform for cryptographic smart cards. But what does it mean? What the open means here? There are on-card applications called applets, which are compiled into Java card bytecode, and then they are executed by Java card virtual machine. So you do have some portability between the cards produced by different vendors, different manufacturers. So with this respect, it's open. There is some public API to facilitate the cryptographic functions frequently necessary to be used on these smart cards. Like if you like to create a elliptic curve digital signature, you need to first set curve parameters, then you can generate a key pair, and so on. So these are public and everyone can use them. But the implementation of these public API methods are by specific card vendor. And the source code is not available, so it definitely fits into black box scenario. So our question for a smart card is the primality testing correctly implemented? If they are using Miller-Rabin, are they selecting witnesses randomly? Are they using enough of them? And the second question is, if the primality testing is correctly implemented, is it used where it should be? So first of all, we know it must be implemented. because smart cards do support RSA key pair generation, and they definitely need to be able to generate prime. So we know it's there. Second thing is, in public API, there is no method, something like is prime. So we can't just directly call some parameter and check whether it's prime or not. So we somehow need to trigger the primality testing indirectly. Maybe we're setting the curve and the subsequent key generation. With respect to second question, is it used where it should be? If it's not used, we may end up with doing operations over the curve with some parameters not being a prime, and as a result, one can recover the prime key. So the very condensed idea of what we are doing is that we will first indirectly trigger the primality testing. So we will generate a pseudoprime of particle form. We will call the method that is expected to do a primality testing, and then we will observe and analyze resulting error. We are submitting pseudoprimes. As a result, we shall get the error, this is not a suitable argument, a legal value. But it's not simple. The problem is that the card is a black box, and we can't just separate the primality functionality. The card itself can reject our pseudoprime parameters for a variety of other reasons, and we can't easily recognize this from the error returned. So as a result, we can get false negatives. We can submit the pseudoprime, we will get an error. We will think that they are doing primality testing properly, but in fact, it failed because of some other reasons. They are not doing primality testing properly. Let's summarize our contribution. So we propose systematic methodology how to analyze whether the primality tests are done properly inside the black box devices, or also black box implementations where you do have just a binary implementation. We constructed several new methods for generations of domain parameters for Diffie-Hellman and digital signature algorithms and their elliptic curve versions, which do have everything correct except for one parameter being composite. We practically verified the approach on the smart cards from several major vendors, smart card vendors. We also proposed a mathematical attack against the elliptic curve digital signature algorithm with the assumption that the field is not prime, but instead it's composite. And because we found issues with during the verification on real smart cards, we compiled a list of recommendations what shall be fixed. And we open sourced our testing toolkit so everyone can do this on their own implementations. And in paper we fit just part of the results. You can find more visiting this link. How do basic testing setup look like? So we first construct or generate the pseudoprimes and other composites. That's relatively easy. What is way more time expensive is to generate then domain parameters for these cryptosystems that are utilizing these pseudoprimes generated above. And this took us several days, some computation of large grid of CPUs. Then when we do have these domain parameters, we will start setting them and triggering the primality tests indirectly with these composite parameters. So for example, we will set the field, and which is composite, shall be prime, and then we will call generate key pair, and we will look what are the issues with the behavior of the card. We are looking at error, but not only that, we also look at the response time, whether the card responded at all, whether it's cycling indefinitely, and so on. With the smart cards, you can't count just on one attempt and expect deterministic behavior. So we are repeating the experiment 100 times with different inputs, with different domain parameters. Each input was tested 10 times to capture some error or non-deterministic behavior. And when if the composite domain parameters were accepted, we will just run the attack to see whether it was for real. For the pseudoprimes, we used Arnold's method with 3 factors, so the composite is having 3 factors, and it's designed to maximize the number of bases the witnesses fooled at a given bit size.
For other composites, we generated the composites with various numbers of vectors and also various smoothness level. We used the following bit sizes to capture the commonly used bit sizes. And we are covering 4 scenarios where we are replacing prime with the composite. Depending on the situation we're using, whether it's elliptic curve based or the classic one, and whether it's order of generator or it's cardinality of base field or multiplicative group, respectively. We took our methodology and analyzed the real smart cards. You can see the list of them on the left side. And this slide shows you results for ECDSA algorithm for 2 scenarios. One is setting the cardinality of the field, E, and the second one is setting the order of the group, N. How to interpret these results? First of all, if it's green, it's good. We haven't found any weakness. If it's red, it's bad. It means we are able to supply the composite where it should be a prime. And if it's yellow, this means it's not rejecting value, but it's cycling or something like that, so we can't get out the results we need for successful attack. But nevertheless, it seems that the card in that scenario is not working properly. It's not rejecting composite numbers. How to interpret acronyms? Okay, it's clear. This means it was accepted by a card. EL means the card emitted a illegal value error, and that's desired error, because if the submitted value is composite, it shall be rejected and shall be rejected with illegal value. So that's what you like to see in case of composites. If you will see OK, where the composite was submitted, this means that we were able to submit the composite, run the whole computation, get the signature out, and as a result, we can attack the implementation, get the private key. So this is red. And if you will see cycling, muted, and some other exception, this means we submitted composite, it was somewhat accepted, but then the card crashed, cycled, we were not able to get something that is useful for performing the private key extraction attack. So the issues discovered were responsibility disclosed to affected vendors during the summer 2019. And the most surprising result for us was that very likely the cards are not performing any primary tests on these parameters at all. There is likely exception, Athena ID Protect card, but the rest of them likely seem not to be performing primary tests. Some composite numbers caused other errors than illegal value than the expected one, and our explanation for this is that the card do have some assumptions used during the computation later on, during the computation signature, during the key generation, which is broken because the number is composite. It's not prime anymore. So their algorithm for signature works only when the particle domain parameter is prime. If it's not, it breaks later during the computation. Also, you may say, okay, let's then just fix the issue by adding additional check before the parameters are set by the application running on card, by the applet. Before it's set, we will just call isPrime method, and if the result is true, yes, this is prime, we will just set it, otherwise we will reject it. But the issue is there is no isPrime method in public API. Implementing Miller-Rabin in a custom implementation on card is really costly, so it's 2 times expensive. So as a result, one needs to trust the supplier of these parameters. Basically, this removes one layer of defense. It also enables man in the middle to fiddle with the parameters if they are sent. Also, if someone is mounting fault induction attacks, they are potentially able to perform faults into the domain arguments in the buffers where they are stored. And it's also difficult to patch this for already deployed cards, because for most cards, the implementation is burned in ROM, so it can't be updated. And so takeaway from this is it's not directly exploitable if you are not able to do fault induction or in the middle, but it's removing one layer of defense from the place where an ordinary developer would expect this to be, and the developer of the applet has no means how to substitute for this missing functionality. The important question is, what is the real-world impact? Is the attack scenario even relevant? Because what we are saying is that the attacker needs to somehow trick applet to call methods setting these composite domain parameters. And the question is whether this is realistic. So domain parameters are sometimes sent and are set dynamically. For some scenarios, they are just fixed and stay same forever. But for some scenarios, they are set dynamically. So in TLS up to version 1.2, X509 certificate format allows for public key to hold also full domain parameters. And the suite of protocols for electronic passports allows for transmitting these domain parameters. So there are scenarios where these parameters are transferred and set dynamically. And as I already mentioned, the fault induction attack on the buffer holding these domain parameters can cause the value to switch, become composite, and as a result, the attacker can then attack and extract the private key. As I already told you, for most situations where the domain parameter is composite instead of prime, the attacks are already known, and it's some variant of classic Pollig-Hellman attack. For ECDSA with a composite key, we are not able to find any, so we designed one. Basically, we use the adapt method, which reduces the discrete logarithm problem over the big curve to easier, smaller, and faster to compute discrete logarithm problems over the smaller curves. And then we compose them and solve and extract the private key. And this is realized by elliptic curve version of Chinese Riemann theorem. If you're interested, read the paper, please. Given the issues found, what are our recommendations? So first one is definitely require full domain parameter validations, including all the primary tests of all prime parameters. So this is already specified in standards like X962. So just use it. Second thing is to use strong parameter tests which do not have any known pseudoprimes, either Miller-Rabin with random basis or potentially even Bailey PSV primary tests. Jancar version 3.1, which is the newest one, already do have support for named curves, which means you as a developer you are not setting the domain parameters separately. Instead, you are just saying, I like to use this particular curve, and then all parameters are set. So this is already part of the specification, but the issue is it will take long before it's supported by majority of cards, so some speed up of the adoption is necessary. And the second thing is this will not mitigate all the situations because the fault induction takes still place. And it would be nice to have a primality method in the public API, because then you can have this as additional layer of defense. Nowadays, you can't. To conclude, the fact that primality testing based on weak implementation of Miller-Rabin algorithm can be fooled is well known, and there's a body of interesting research showing that this is a real-world problem in white box scenario where you do have source code of targeted implementation, and move this into the domain of black box device where you are missing the source code. And we designed a suite of methods how to generate domain parameters that are seemingly correct, but are composites in sets, and then performed extensive testing of cards by major vendors. And the surprising result is that the primality of ECC parameters is mostly not tested at all by current smart cards. There are some exceptions. As a result, if the attacker managed to change this domain parameter to be a composite, it's vulnerable and can extract private key. The issue is hard to fix for already deployed smart cards because the implementation is in a code and baked in ROM, read-only memory, which means it can't be updated. What can be updated is the code of applets doing setting of these domain parameters. But the issue is that this code don't have access to primary testing, so there is no prime method in public API, unfortunately. So as a result, the card must trust supplier of these parameters, and if there is malicious actor on the other side as a supplier, or there is man in the middle, or there is some fault induction attack, you can end up using composite parameters. Solution: just perform proper domain parameter validation, or use neighbors where you are not setting the domain parameters yourself. And also, if you're using Primality testing algorithms, use the strong ones, ideally these that don't have any known pseudoprimes. That's all from our side. We're happy to take questions. Thank you.